So in the last module we discussed the total heat transfer rate for a single unit of single fin with attached lateral fins. So now you can think of this as a hexagonal duct array, but one can also do the same idea for square array or a rectangle array and so on, where you take, we consider this as one unit cell and so develop expressions. So all these expressions that the expression given here is accounting for all the different shapes, that is the square, triangle, hexagon and the even the rectangle fins. So what we are going to do now today is that we took TF in a typical single fin heat transfer that is discussed in lectures. We usually use TH and T infinity. T infinity is treated as constant, but here we are not treating it as constant. We are going to treat it as a function of length or the flow length, x being the flow direction, and we are going to discuss now how to obtain this expression for TF. So moving forward on that aspect today is that we are going to take the fluid side energy balance or the fluid side enthalpy balance, the fluid side heat transfer. If I take a single duct of a hexagonal duct, for example, then I know my energy or sensible heat rise is nothing but m dot, which is mass flow rate times specific heat times the temperature rise, and this is, you can think of it as some kind of control volume. You take a, if I look at the side view of it, this delta dTF is this temperature rise in a simple, but it has two units of heat transfer, which is one contribution coming from the fins, if there is heat transfer from the fins, and then there is a heat transfer from the bottom of this plane, and that is what is acknowledged here, Q wall. This we call it as Q wall versus this being the Q of a single fin multiplied by number of fins Ns in the unit cell. Then we get the total heat transfer from the fin and the wall. So that is balanced by the temperature rise in the fluid stream. So that is what is acknowledged in this equation. So we have calculated for the, in the previous slide we calculated heat transfer rate for a single unit cell. Then in the here we multiplied by number of unit cells. So for example, if we go back to, so what we did was to calculate for a single fin like this. Now if I want to find the number of unit cells, then I have to take, this is 1 unit, so 2, 3, 4, 5, 6, 7, 8, 9, 10, and this half and another half, 11. So you would end up having 11 units in this case if this was discussed, the rectangular fin. But so that number of Ns is number of unit cell. So in order to calculate the bottom wall heat transfer, where the fin is not in contact but air is in direct contact with the bottom of the wall, bottom face, that is this guy. So this is acknowledged as Q sub W, and this is the wall from the heat sink base. So that we need to find another heat transfer coefficient, that you can use either a parallel plate or keep using the same local heat transfer as a duct heat transfer coefficient. So when we talk about in the previous case this local heat transfer, this is nothing but if it is a hexagonal duct, we use fully developed flow expression for a hexagonal duct configuration. If it is a Square, we use this relationship for square Nusselt number for fully developed flow. If it is a triangle, we take the fully developed flow expression for triangle fins of triangular ducts, cross sectional ducts. So that is also tabulated in the next in the upcoming slide. We will discuss that. Here H, one can use the same triangular fin expression, or one can take some additional analysis and take into account more accurate heat transfer coefficients. But for in this module, we are going to use the same expression as that of the triangular duct or whatever duct that we are modeling. And W is the width minus the number of unit cells. CW is another constant that arises just to take into account the area in order to find out what is the area of the bottom plate. So, if I want to find this distance, then I need to remove the thickness of this fellow, and that is what is taken into account in the form of CW times T. This factor takes into account the thickness of the fin. So, that subtracted into the number of fins minus the width gives the open area of the bottom plate per unit depth, and then T wall is the wall temperature that is kept constant, Tf minus Tf. Tf is yet to be found. We plug this into these expression, write the mean fluid temperature at any given location. We look for Tf, and that if we rewrite, we get Tf as a function of x is equal to T wall, which is known, minus T wall minus T inlet into exponential of minus x by L star. What is this expression? Where did inlet come from? Is that at x equal to 0, the temperature of the fluid at x equal to 0 is T inlet. So, using that as the solution, we obtain the solution for Tf as this. You get the local fluid temperature as this, and you can see that you are getting an exponential dependence, which is expected for any isothermal wall case. And L star is obtained by grouping all these other factors into this, and that is this expression, this long expression. It's essentially same. If you plug this into this equation, and you will end up getting a dTf by dx equal to this, and that expression upon differentiation you end up getting this. And once you calculate L star, group them all, you get this expression, and from this you can calculate for x equal to L, setting 0 to x as 0 to L, that is for the entire length, you get the total heat transfer rate equal to rho times u mean is the mean velocity that is entering the heat sink, Cp height times width into the temperature difference T wall minus T inlet into 1 minus 6 min. This, if you rewrite in terms of resistance, this is going to give you delta T, which is this fellow, divided by Q is going to look like 1 by m dot Cp into 1 minus exponential of minus L by L star. This is nothing but NTU, just written in a different fashion. This L by L star can be rewritten in terms of HF into A divided by m dot Cp. However, it is written in this fashion, but it is essentially representing the number of transfer units. So, again we get even after this entire whole scenario of going through a different variety of derivations, you end up getting the same expression for heat sink, which we discussed using heat exchanger theory before, and it is equally valid, is 1 by m dot Cp into effectiveness. This is nothing but effectiveness of the heat sink. So, we discussed so far how to derive heat transfer rate for an array of ducts. Now, we look into how to model the pressure drop. Modeling the pressure drop is simple, and just take the friction factor and just make use of this factor of 4 comes from Darcy to fanning friction factor conversion. So, you get a pressure gradient from the standard formulas. These Cf and Cas are essentially constants just to take into account different shapes and structures, geometries, that essentially square, rectangle, triangle. So, and we make use of maximum velocity because there is an array of ducts that we are encountering. The mean velocity that is entering is going to increase as it enters, because there is a fraction of the flow area is occupied by the walls. So, we make use of that and calculate local fluid velocity in terms of Umax and substitute that to get the maximum. So, then we using the as we discussed, it can be relaxed, and the table here gives you the square is equally valid for rectangle as well as for square, the parameters Ca, Ch, N, Cf, Ct, and these are all used in the expressions developed so far. For rectangles, the thickness and the FRE Nusselt number relationship are given here. We can't use the Nusselt number relationship given here because these are meant for those square and triangle and hexagons. For rectangles, you have a function of alpha. Alpha is nothing but the aspect ratio of the rectangle. So, for that you need a different expression for FRE and the NU, and we make use of this into the previous expression that was developed in the previous slide. So, with that we can see and go ahead and plot this, and you see that the triangle pack gives you as a function of cell pitch. Cell pitch is nothing but this LW is kept as a varying parameter, and if you plot that cell pitch as a function of thermal resistance of these different shapes, you find that triangles are worse performing because they pack more for a fixed pressure drop constraint. Here the pressure drop is kept constant, and for a fixed pressure drop constraint, because there is lot of surface area, because triangles have very high packing density, that the surface area is very high. So, for a fixed pressure drop constraint, you have very large triangular heat sink being the worst performer in terms of thermal resistance, then the square, then the hexagon. But if you go to rectangles, this is an example for rectangles of aspect ratio alpha equal to 4. And if you go to even higher rectangular aspect ratios like alpha equal to 6, they perform better and better. However, a rectangle tending to infinity, you end up getting parallel plate heat sink. So, what you see is that parallel plate heat sinks are quite competitive, even though we have done a very big change in the geometry and so on, that the rectangles and parallel plate heat sink can be even more competitive here. But what we find is the rectangle fins tend to be better in terms of performance among the shapes that we discussed. Moving on, so the aspect is that one of the reasons why these heat sinks had some issues is that the lot of surface area was increased, and whenever you increase surface area, your pressure drop also increases, which is the skin friction coefficient. Also, within the heat sink itself, there may not be sufficient mixing, and the flows that are going through the bottom duct may not be will see much hotter temperature because it is closer to the hotter wall, while the flows going through the top duct will see lower temperatures. So, one has to mix these two to get a better performing. So, introducing slots or doing something else like this may increase the performance. However, one other additional concept that exists to improve the performance of heat sink is the so called flow stabilities, that is creating unsteadiness in the flow. And at low Reynolds number, the goal of any of these unsteadiness is that, for example, let us look at this shape here. If we put, these are called slotted heat sinks, where a longitudinal fin like this is cut intermediately to create separation zones. So, the flow enters, there is some kind of separation here, and as it exits, it starts to influence, there is an impingement zone depending on the spacing between these fins, it will start to influence the upstream flow itself because of separation, and it creates now the contact of the boundary layer that is developing will be affected by this, and it creates an unsteady effect. And so the goal of many of these unsteady flow or laminar flow instability based heat sinks is that they want to achieve as low a Reynolds number as feasible to achieve the flow unsteadiness. And this is what we are going to discuss in the next part of it, the last part of the heat sink module. And the next one we are going to discuss now is the foam heat sink, and then we will go to the laminar flow instabilities subsequent to this. What are foam heat sinks? Foams are, these are metal structures, reticulated structures that have continuous metal pads as well as flow pads. The flow pads in the array of ducts we discussed is that the flow pads are not interconnected. Only when a slot was made, it can become interconnected, and that too only in the vertical sense. Here in porous heat sinks, the porous metal heat sinks, the flow pads are interacting. The pores are connected, interconnected, and the metal path is also continuously are also continuous. So heat will flow simultaneously versus flow will also go through these porous areas and pick up heat from the metal wall. There are many varieties of metals are being foamed, all the way from aluminum to stainless steel or even nickel superalloys. So what we are going to look into is only a simple foam geometry like aluminum or copper based. And one of the main advantages is that when you do foaming, that specific surface area per volume increases dramatically compared to some of the other geometries that we typically encounter in heat sinks. With that increase in specific surface area also comes the situation that when there is flow, you may encounter new types of problems in terms of penalties in terms of increasing foam drag or skin friction and some separation effects causing more pressure drop to occur. But if they are done correctly, but foam heat sinks can also be used as multifunctional materials. For example, they can be used for absorbing sound in electronics cooling setup. The sound created by fans is a nuisance, and if there is a way to absorb, if a heat sink can absorb both the sound as well as dissipate heat within the same functional volume, then it is a very big advantage. Similarly, one can use these foam heat sinks for heat dissipation as well as energy absorption, like impact absorbers or shock absorbers in a car or any mobile EVs or anywhere where there is a absorption as well as heat dissipation issue that occurs. So they can be they are treated as very viable multifunctional materials, these foam heat sinks. We are going to look at a very simple air cooled heat sink concept, but this approach can be used for even for heat exchangers applications. And some of these foams have been used as heat pipe wicks for nickel heat pipe wicks for high temperature space applications, for example cooling the blunt nose of an aircraft and so on. So we will look into the air cooled heat sinks using the same model that we discussed, is just that R equal to m dot Cp into effectiveness. The goal is to figure out what is the effectiveness of these heat sinks and in terms of geometric parameters and how can we approach. So as we discussed, we are going to make an approximate model. These are not meant to be accurate, they are meant to be approximate models that work within 10 to 20% of the pressure drop or the measured pressure drop and experimental heat transfer rate that can be predicted using simple models. So here is an example where if you had a foam heat sink and let us say this is the T base and let us say this is coming in at some temperature T in, then how do I go about calculating the resistance of such a foam heat sink? And that is what is shown here, 1 by m dot Cp into effectiveness. The effectiveness, as we discussed previously, is nothing but 1 minus exponential of minus NTU. NTU is number of transfer units, and number of transfer unit is eta into HSF, the surface area. This is the, we'll discuss this heat transfer coefficient, and the area, surface area is A effective, m dot Cp is your mass flow rate times Cp, specific heat. This HSF is called local interstitial heat transfer coefficient. In a foam type structure, that people can get confused with multiple discussions, where one may refer to heat transfer coefficient from the wall itself, and that is also a heat transfer coefficient. But what we are talking about is the interstitial heat transfer coefficient, that is at a pore level, what is the heat transfer coefficient between the wall here and to the flowing fluid within the local pore. This is also measured experimentally. This is typically an empirical parameter that is measured, and that heat transfer coefficient is required to do this modeling, and that is what, but it is for standard stochastic foam. Already heat transfer coefficients have been reported, and we will make use of that. And also we need to figure out a way to calculate the surface efficiency of these foams, and that we will do in the upcoming slides. And the interstitial heat transfer coefficient, we are going to make use of the correlation given by Kalidi and Mahajan in their paper, and so that has Kf is the ligament or the metal fiber. This F is not fluid here, it is the fiber. It's the fiber heat thermal conductivity, and Df is the strand or the fiber or the ligament diameter. So this is often called as the fiber, this guy, or a strand or a ligament. It usually has a cross section of this nature. The cross section of many of typical foams, it can vary, but typically it is triangular in cross section, that it has a, because of the way they are formed, it has a cross section of this kind. So the goal is to figure out an effective diameter for this cross sectional area and effective diameter, and that is what is referred here as the fiber or strand or the ligament diameter. Then we write the Reynolds number is referred here, is a modified Reynolds number, is the density times u, the velocity, the local velocity, the fiber diameter divided by the dynamic viscosity, and phi being the porosity. Phi is nothing but the total pore volume or the empty space or air volume divided by the total volume of the heat sink. So this is the expression for phi. This air can be pore or the empty space divided by the total. This total consists of both air plus solid. So that is the expression for V air divided by V total, and this correlation is valid for the porosity range of 89% to 97.3%, and Reynolds number based on permeability. What is Reynolds number based on permeability? It is given by the expression rho u square root of K divided by mu. K has units of meter square. It is a geometric constant for any porous media, and it is usually reported, and in Kalidi and Mahajan's paper they have reported for stochastic foams a variety of permeability values, and also empirical correlation is also given for these foams. So making use of that correlation, now we need a way to calculate the fin efficiency. So we are going to calculate a fin efficiency here, and that fin efficiency we are going to use an approach developed by G.I. Taylor for modeling porous media for fluid flow. And what we are going to do is that there is going to be a porous media. If this is my foam, I am going to convert that, there is a 3-dimensional part of the foam. I am going to convert that into some kind of equivalent solid fin. How do I do that? Is that we are going to treat this solid fin, and in the next page we will discuss that. So, we are going to transfer that into a solid fin in some kind of parallel plate mode. Instead of foams being distributed like this, we are going to treat it as if the solids were somehow merged into making some thickness TPF of the foam into a solid fin, and there is space for airflow to happen. And then now we get a parallel plate type structure. So, from that we get a thickness relationship. From this thickness relationship, plugging into a standard efficiency relationship will fetch us the surface efficiency. And this is what we are going to do in the next module. So, we are going to take this method of transformation of porous media into equivalent solid fins, and from that we are going to get a surface efficiency. Once we know the surface efficiency, going back here, we can calculate, we know surface efficiency. Once we know how to calculate, we already have a correlation for heat transfer coefficient. Surface area can be estimated from manufacturer's data or by your own. Mass flow rate is given or assumed to be known, and Cp is known. So, from this we can calculate an effectiveness. From this effectiveness, then we can calculate m dot Cp. So, in the next module we will discuss how to calculate that surface efficiency, and we will discuss how to calculate the overall foam resistance, heat sink resistance. Thank you.